Okay, for the last talk of Tuesday, it's a pleasure to welcome Josh Sussan, who will talk about PDG and Zigzag.
Okay. Yeah. Thanks for the invitation. Thanks everybody for coming. So I'm going to be talking about relatives of the zigzag algebra, not the relative we saw in the previous talk, but maybe some simpler relatives, and how to import some Pdg theory from the lectures that we saw from Shiyu into the story. So maybe just a quick brief outline. I don't know how much we'll get to. So the first section will be this algebra AN, which is essentially the zigzag algebra. Then we'll move on to its Koszul dual, AN shriek. Then we'll look at a deformation of AN shriek. This is I'll call the deformed Webster algebra, which we also saw a little bit of in Joel's talk. Then I'll move into a kind of a quick overview of Pdg theory, a review of what we saw in Chiyu's talks. Then we'll import the Pdg theory to this AN shriek case, then Pdg theory to this deformed Webster case, and then maybe some work in progress about returning back to the Pdg story with the original zigzag algebra. Okay, so this will be kind of a review for many of you here, but I'll go through it. So first, this first section is algebra AN. So this is a quotient of this of the path algebra of this linear quiver where we have n nodes, and the relations are 1 to 1 is equal to 0. So that just says that a loop at the first node is equal to 0. The second relation, I plus 1i is equal to I minus 1i. This is that a loop to the right is the same thing as a loop to the left. And then finally, this last relation says that taking 2 steps to the right or 2 steps to the left gives us 0 in the algebra. And so this is a graded algebra. The grading convention we'll take here is that it's graded by path length. So each edge is has each path from like I to I plus 1 or I to I minus 1 will have a grading degree 1. And there's also n idempotents. Those correspond to the stationary paths at each of the n different nodes, and those each have degree 0. So maybe just a quick note to connect to Lee theory is that the category of graded modules over this algebra AN is equivalent to parabolic category O for GLN, where this is corresponds to the parabolic subdata, the parabolic data of S1 cross Sn minus 1 symmetric group, the Weil group for GLN. Okay. And so I want to be talking about braid group actions. And so for this algebra AN, I want to introduce these projective modules AI. So remember, so when I put this parenthesis I, that just means the idempotent of the path of length 0 at the node I. So AI is a left projective module. It's indecomposable. So we have n indecomposable projective modules. I goes from 1 to n. And this is a fairly simple algebra, and you could check the following facts fairly easily, is that the endomorphism algebra of this first projective, A1, is just one-dimensional. The endomorphism algebra of the other projectives are two-dimensional. The Hom spaces between neighboring projectives is one-dimensional, and the Hom spaces between far-away projectives is equal to 0. And I don't think I mentioned this in this first section, but I should say what the zigzag algebra is. It's essentially this algebra AN, but we're taking the idempotent subalgebra where we ignore the first node. So it's generated by the idempotents for the nodes 2 through n. Okay, and that corresponds to these are nice projectives from a categorical braid group action perspective. Okay. And so so for these nice projectives, these spherical projectives, which have endomorphism algebra of degree 2, we could set up these complexes of AA bimodules. So we have this complex TI, which is AI tensor IA. So that's a AA bimodule. And then there's a map, just the simple concatenation map, multiplication of the factors to A viewed as a bimodule over itself. So manifestly a bimodule homomorphism. And then there's a more complicated complex, Ti prime, which goes from A as a bimodule over itself to AI tensor IA. And explicitly there's a formula given here. One has to check that this is actually a bimodule homomorphism, but it's not so hard to verify this. And I should also say that most parts of this talk, I'm going to omit some grading shifts which occur here. Okay, so so the kind of an important theorem in the subject is due to Havanov and Seidel, and also independently Ruquier and Zimmerman. So we have these complexes of AA bimodules, and one could check that on the homotopic category of graded modules over A, that Ti and Ti prime, I goes from 2 to n, they satisfy categorical braid group actions. So Ti and Ti prime are inverse complexes of each other. Ti and Tj commute if I and j are far apart. And then you have this braid relation, Ti, Tj, Ti is isomorphic to Tj, Ti, Tj if I and j are adjacent. So just kind of a quick remark about the proof of this. So to check that Ti and Ti prime invert each other, these are all fairly explicit calculations. So here Ti tensor Ti prime. So we have the complex for Ti on the left and the complex Ti prime on the right. You do this tensoring, and you get a 3-term complex. And so in the second to last line, what you use is that IAI, which is really just the endomorphism algebra of AI, is 2-dimensional. And then if you kept careful track of all the maps, you could see how to contract out various pieces, and all you're left with is this bimodule A, which is corresponds to the identity functor. So the fact that Ti and Ti prime are invertible functors really just corresponds to the fact that the endomorphism algebra of these projectives is 2-dimensional. The fact that the Hom space between projectives which are far apart is 0 corresponds to the fact that Ti, Tj commute if I and j are far apart. And the most complicated relation that Ti, Tj, Ti is isomorphic to Tj, Ti, Tj uses the fact that the Hom space between neighboring projectives is 1-dimensional. Okay, and so just a couple of remarks. The section is that so Havanov and Seidel in their paper, they prove that this action is faithful. So this is a little bit surprising because this categorifies the braid group, the Bureau representation, and then the level of growth in the group, the action is not faithful. So you get some extra information from categorification. And so as I mentioned before, this is related to parabolic categorio, a fairly easy parabolic subcategory of it. This is true, these braid group actions exist for more general parabolic data. So Stroppel extended this braid group action to get a link homology, which recovers Havanov homology. Okay, so we're just seeing a shadow of much more interesting topological constructions in categorification. Okay, so now I move on to the second section, which is AN shriek. So this is, again, the underlying quiver is the same. It's this linear quiver with n nodes. And relations are similar. A loop at the node 1 is equal to 0. A loop to the left is equal to a loop to the right. But we omit this last relation that 2 steps to the left is 2 steps to the right, which is equal to 0. So this is a bigger algebra. So this is AN shriek. And this algebra AN shriek is Koszul dual to AN. And well, you could see this in various ways. From Koszul duality of category O, we get that this category AN shriek of graded modules is equivalent to singular category O. Now the data for the singularity, this generalized central character is S1 cross Sn minus 1. Okay, and so one could ask about a braid group action on this side of Koszul duality, and this shouldn't be surprising at all, but there is a braid group action, of course, but this doesn't come from projectives. You can see this fairly easily because the Hom space property satisfied by the projectives for the algebra AN don't hold for AN shriek. In general, the endomorphism algebra, the projectives grow as you get further down in the quiver. Okay, so you only have actually one spherical projective here. But for Koszul duality, we know that projectives and simples should get exchanged. And so we should consider instead the simple modules for AN shriek. Okay, so the simple modules for AN shriek are very easy. This is, we let all the simples are one dimensional, and we have a simple for each node in the quiver. So we let Li be the one-dimensional space spanned by this vector Vi, and the idempotent I acts as the identity. and everything else in the algebra kills this vector vi. So this is a left module for A and shriek. We similarly would have right modules. Okay, and so these simple modules should give rise to a braid group action. In order to construct this braid group action, one has to construct a projective resolution of these simple modules. And it's not so difficult to construct these projective resolutions. So for the nodes 1 through n-1, the projective resolutions look as follows. So in the rightmost degree, we have this projective module. So here A is A and shriek. So we have this module AI. Then in the next degree over, we have the neighboring projectives. And one step over, we have we get back the module AI. And the maps in this projective resolution are just given by multiplying by these paths of degree 1 from one node to the next. Okay, and I'll just mention this, even though this is not important for the story of this braid group action. This node Ln, this projective Ln, which is kind of like the projective A1 from the previous section. This has a different resolution. It's a little simpler. It's just an-1 into A. Okay, so from these projective resolutions, one could easily calculate X properties between these simples. So from this note at the bottom about the projective resolution of Ln, one could see that the X algebra of Ln is one-dimensional, and the X algebra of all the other simples is two-dimensional, okay, which is what we should expect from Koszul duality. It's this two-dimensional algebra kx mod x squared. And the X algebra between neighboring simples is one-dimensional. And finally, the X algebra between distant simples is 0. Okay. And so one could form, in an analogous way for the previous section, complexes of AA bimodules, except there'll be one big difference in a second. So first you have this braiding complex Ti, which goes from A as a bimodule over itself to Li tensor Il. So this is projection onto the simple bimodule. And then you have a complex Ti prime from Li tensor Il into A. But one has to work in the derived category here. You can't find a bimodule homomorphism in the normal category of AA modules. One has to take a projective resolution of at least one of these LIs to actually cook up this map. So we're forced into the derived category. Okay, and one could very explicitly construct this map iota. So then, well, one could see either just directly from Koszul duality or from just long but doable calculations here, that as functors on the derived category of graded modules for A and shriek, that Ti and Ti prime satisfy these braid group relations that we saw earlier. Okay. Okay, and so now moving on to the third section, I call it deform Webster algebra. I think Ben calls them KLRW algebras, a deformation of these KLRW algebras from Joel's talk. So first, what about the Webster algebra before deformation? So this algebra A and shriek, it has graphical presentation that we saw a bit about in Joel's talk. So I'm looking at a very special case of these Webster algebras. First of all, we're looking at sort of categorification of SL2 theory. And we're only looking, so we have n red strands. So this corresponds to the n nodes in our quiver. And representation theoretically, this corresponds to the fact that I'm taking the tensor product of the standard SL2 representation n times. And I'm only considering one black strand. So this corresponds to the fact that I'm looking at maybe the second highest or the second lowest weight space of V1 tensor n. Okay, so this simplifies a lot of things for this talk. Again, these things could be done in greater generality. Okay, so what are the rules for this algebra? So first, red strands aren't allowed to cross. Black strands carry dots, and a black strand on the left is equal to 0. So that's the so-called cyclotomic condition. And what are some more graphical relations? So a black dot slides through a black-red crossing, and both types of black-red crossings. And finally, if you have a black-red double crossing, they separate at the price of picking up a black dot. And I should say that, so this is, again, this is graded. The black-red crossing is degree 1. Black dots have degree 2. And multiplication in this algebra is given by stacking from bottom to top. It's concatenation. And so the isomorphism between A and Schriek and this graphically defined algebra is given as follows. So the idempotent I, this is a path of length 0, stationed at I, corresponds to this, this diagram where all strands go directly up, and the black strand is positioned ith from the right. The path I plus 1 takes a black dot, takes a black strand in the I plus 1 spot on the bottom to the I spot up top, and the path I plus 1 I takes a black strand on the bottom left to in the spot I to I plus 1 up top. Okay, so one could check that this is the isomorphism given by the algebras, and the various relations we saw in this algebra and Schriek manifest itself in these relations that we saw earlier. Okay, so now this algebra has a deformation. So let me call it W bar. So we introduce extra generators where now red strands carry dots. And now we have to add some extra relations and deform the earlier relations. So red dots go through crossings, and now when you have a black-red double crossing, they separate again, and you pick up the black dot, but now you pick up this deformed term of a red dot on the red strand. And I should say that I'm actually, for just for simplicity, I'm going to omit the cyclotomic. Oh, sorry. Right. So when we omit, I'm going to omit the cyclotomic relation for simplicity. I'm going to call that resulting algebra W. I should say the algebra W bar actually describes a category of singular sorgal bimodules. Okay, and so now what about a braid group action in this deformed setting? So this is, again, this is a deformation of A and Schriek, and maybe there exists a braid group action here, and there does. So we want to introduce some bimodules for W. So I'll say Wi. So these bimodules look a lot like the algebra, except this bimodule Wi, we have this thick red bar connecting the I and I plus first spots down below to the I and I plus first slots above. So this is what I call kind of a red background. And then we have one black strand. So the one black strand could be kind of doing its thing. It could go like this, or it could do various intersections. Okay, and so that's what generators of the bimodule look like. And what about relations? So, and now I'm kind of just focusing on the interesting part where we're connecting the I and I plus first strands. Symmetric functions up top in the red dots flow through the thick red strands. So this first equation up top is saying that the first elementary symmetric function up top is equal to the first elementary symmetric function down below. And the second equation is that E2 goes down to E2 on the bottom. Okay, and what about black strand? So let me go back for 1 second. If we have no black strand, this actually looks like a sorgal Bott-Samuelson bimodule, corresponding to a generating object in the sorgal category. Now, if we have this now incorporating the black strand into this picture, so the black strand flows through the picture. If it goes through the bottom two legs, it can go through the middle thick part, and then it goes up to the top, along with its mirror image. Okay, and so we impose those extra relations along with the relations from this deformed Webster algebra. Okay, and so now we could cook up bimodule homomorphisms. So first we have this bimodule homomorphism epsilon I, which goes from the bimodule Wi to the bimodule W as a bimodule over itself. And this is just sort of an unzipping map. It takes the thick red strand and separates them into two thinner red strands. And then you have a map iota I in the other direction from W to Wi. And So if there's no black strand in between the two neighboring, between the ith and I plus first red strand, this is a familiar map between sorgal bimodules. So you get a dot up top, up on the upper left, minus a dot on the bottom right. But now we need to take care of the case where we have a generating element in the bimodule where we have a black strand in between the two red strands. And after some fiddling around, you could properly say that you have the black strand swings to the right of the thick red strand minus swinging to the left. Okay, and one checks that these are bimodule homomorphisms. Okay, and so so now we have these bimodule homomorphisms, and so now we have these. We could form complexes Ti, which is Wi to W, and Ti prime, which goes from W to Wi. And with Havanov, we proved that in the homotopy category of W modules, that the complexes Ti and Ti prime satisfy braid group relations. And so something slightly interesting to note is that when working with A and Shriek, we were sort of forced into the derived category. With this deformation, we're able to stay in this homotopy category. Another way to kind of think about this is that it's these redotted Webster algebras, these deformed Webster algebras, are kind of a mixture of nil-Hecke algebras along with sorgal bimodule theory. Okay, and so just a couple of more remarks, maybe before the break. So as I mentioned, these algebras are they're just special cases of more general algebras. So this algebra Wn1, where again this n corresponds to the number of red strands, and 1 just corresponds to the one black strand. This could be generalized to W bold dk, where d is a tuple of natural numbers. And one could show that there's a braid group action on the homotopy category of WDK modules. And this was joint work with Havanov, Lauda, and Yonezawa. So these more general algebras, WDK, it's a deformation of an algebra categorifying tensor products of SL2 modules, again, as we saw in Joel's talk. And these algebras have SLM analogs, and Webster proved the braid group action in this much more general context. Okay, so maybe this is a good time to take a break before we get into the next section.
Sounds great. We'll start again at 11:58. In the meantime, question.
Oh yeah, so Monica, yeah, so yeah, the Ti prime satisfy the braid group relations also, because the inverses of elements would satisfy the relations.
Great, just checking. Thanks.
Yeah, sure.
Where did this idea of putting dots on the red strands come from?
I think that these ideas were always kind of percolating in Michael's head, maybe from kind of diagrammatic descriptions of LOT, from LOT algebras, and it's always like trying to marry sorgal theory with nil-Hecke theory, I think.
It's geometrically very natural, right? All these guys are X algebras of perverse sheaves, and this is like turning on equivariance for a torus.
Right.
Yeah. I guess, yeah, that's right.
Borel, which is why the Zirkel bimodules come up.
Yeah, no, I understand.
Borel, if you have something where there's a G action and you look at Borel equivariant things on it, you automatically get a Zirkel bimodule action. But this is, I'll talk about this in my talk tomorrow. So
okay.
There are many answers to this question.
Right. So in general, if you had thicker lines, you should be using the appropriate parabolic invariant. Okay.
Yeah, and I don't know, Ben, if you're going to talk about Delta and Setlin modules, but it also comes up as you showed in your
part of the plan.
Yep.
To those who are not familiar with this notation, the dots in terms, is that shifting the degrees, or
you're asking about
the dot really stand for?
I mean, from just a very combinatorial algebraic perspective, they're just extra generators in the algebra. I don't know, maybe Ben could say better geometrically, but degree 2, sorry, was that the question, what the degree was?
So in terms of complex, they're the same thing, but are placed in a different, just a shift degree 2.
Yeah, so there's an internal grading, and so the black dots and the red dots, they both have internal Q degree 2. This is independent of the homological grading. From complex.
Oh, it's independent of homological grading. It's the internal grading.
Yeah, internal grading. Yeah.
Okay, thanks.
So Josh, what's the Koszul duality in this case? What's the dual an in this in deformed Webster algebra? Should it be some equivalent version of an, or?
It's a good question. I don't know off the top of my head. I don't remember how many. I mean, I have to think what HH2 of an is to think about if there are any actually interesting deformations. Yeah, I don't know the answer off the top of my head.
I mean, this is one of these like, deforming corresponds to doing curvature on the other side kind of stories, right? That if you want two nice abelian categories that are Koszul dual to each other, you have to like only keep half the dots, and there are like two different ways of cutting out the dots. That, anyways, yeah.
And it's also like akin to deforming Michael's Havana-Chen-Strappel arc algebras.
But I mean, you see the same thing with Zirkel bimodules, right? That if you want to take the Koszul dual of the category of Zirkel bimodules, you get something kind of complicated on the other hand.
Yeah, right.
Fill half the variables, then you get something that's self-Koszul dual.
Right.
So it's the same.
Yeah, so it should be something, yeah. So it should be something kind of complicated probably on the other side.
And the algebra an at the very beginning, is that the pre-projective algebra of the quiver an?
No, the pre-projective algebra is closer to an shriek, where you so in an shriek.
And at the both ends, if you go around, that should be 0.
Yeah. So yeah, exactly. So for the pre-projective algebra, you would also kill the loop at the nth node in addition to the loop at the first node.
So that's the an. An shrink doesn't have that relation.
Right. An shriek does not have that relation.
Okay,
And the pre-projective algebra is a quotient of an shriek.
Mm-hmm. Yes.
Shall we continue?
Sure. Okay, thanks. Okay, so so the second half of the talk is trying to incorporate some Pdg theory into the story. And I'm sure most of you went to Chiu's talk, so I'm going to give kind of a brief review of Pdg theory, and then we'll start talking about how to incorporate it into these algebras that we saw in the first half. Okay, so again, we saw the main motivation in Chiu's talks. This was an idea of Havanov. So again, one of the big dreams of Crane and Frankel when they introduced the categorification program was to categorify 3 manifold invariants and to construct the 3+1 TQFT. And so in order to categorify these Whitmer-Shitty contrived invariants, one first wants to categorify the place where these WRT invariants live. And so the WRT invariants live in these cyclotomic rings, OP. And in general, you don't have to, in the classical case, you don't have to specialize P to a prime, but for reasons from categorification perspective reasons, we want to specialize the cyclotomic ring to a prime P. So OP is Z adjoint Q inverse mod this P cyclotomic polynomial. For prime P, the cyclotomic polynomial has this very nice form. Okay, and so we want to categorify this cyclotomic ring, and this goes back to Havanov's topological paper. So, so from here on out, we let K be a field of characteristic P. and we let HP be this truncated polynomial algebra, K joint D mod D to the P. And we're taking, for now, the degree of D to be 1. We'll have to change that to match categorification conventions in a few minutes. Okay, so this algebra HP has a unique simple module up to isomorphism and grade shift, one-dimensional. And to fix notation, we let L be the one-dimensional simple module concentrated in degree 0. Okay, and so since we very easily classified the simple modules, the growth in the group of the category of HPG modules is isomorphic to this ring of Laurent polynomials, where the class of a simple module shifted up by R, that's what I mean when I put that R in the angles, goes to the monomial Q to the R. Okay, so all that does is give a categorification of the ring of Laurent polynomials, which is not very interesting because that could be done in many ways. But Havanov's observation was that now let's look at the module HP as a module over itself. And so it has a filtration with subquotients L shifted by 1, all the way up to L shifted by P minus 1. So that tells you that in the growth index group, the class of the projective module is exactly this P cyclotomic polynomial. And so if you want to categorify this cyclotomic ring, you want to kill this projective module. So you want a category where HP is actually isomorphic to 0. And that leads us to this stable category. So we let HP Gmod underline be the stable category of HP modules. So the objects are the same as the normal category HP Gmod, but now the space of maps is cut down. So in the stable category, Hom between M and N is are all HP maps between M and N, but then we kill a certain subspace. So IMN is the subspace of all maps which factor through HP itself. So the identity map from HP obviously is in the subspace. So once you kill the identity map, you're killing the object. So this leads to this lemma, this important lemma of Bernstein and Havanov, which is that the growth in the group of the stable category is isomorphic to this P cyclotomic ring. Okay, and again, more review from Chuyu's talk. The WRT invariant for SL2, one could define it using the representation theory of the small quantum group, which is defined over this P cyclotomic ring. And so we want to categorify modules and algebras over this P cyclotomic ring. And so Havanov outlined the procedure to do this. So we let A be a Z-graded algebra over a field of characteristic P, endowed with a derivation D of degree 1, such that D to the P is equal to 0. So we call A Pdg algebra. If P is equal to 2, this is just a normal DG algebra over a field of characteristic 2. Okay, and so let's let N be a Pdg module over A. So all that means is that N is a module over A, and it also has a derivation, which raised to the Pth power is equal to 0, which is compatible with the derivation on A. So this is just an analog of a DG module. Okay, so now if we take M to be a module over our algebra HP, sort of our ground category, and N to be a Pdg module, if we tensor them together, we get another APDG module. So how does this work? Well, as an A module, an element A and A acts just on the second tensor factor. And what about the P derivation on M tensor N? Well, it's given by Leibniz rule, D tensor 1 plus 1 tensor D. But I should note there's some abusive notation here. D in the first tensor factor corresponds to D in the algebra HP, where D in the second tensor factor corresponds to the derivation D in our Pdg module. Okay, so the fact that you could tensor M and N together to get another Pdg module gives us a functor from HPG mod cross APDG mod to APDG mod. So I should say that endows the growth in D group of APDG mod with the module structure of the growth in D group of HPG mod. But the growth in D group of HP modules, it's just the ring of Laurent polynomials. So we have to go a bit further to categorify modules over OP. Okay, so let's let N prime and N double prime be two Pdg modules over A. And let's let F be a morphism between these two Pdg modules. So it respects the A module structure and the Pdg structure. So F is said to be null homotopic if there's a map H from n prime to n double prime such that F is equal to this sum. So if P is equal to 2, this just says that F is equal to DH plus HD, which is just a normal notion of a null homotopic map between DG modules. So we now let APDG mod underline be the homotopic category of APDG modules. So that just means we take the category of PDG modules and we quotient out by null homotopic maps. Okay, and so Havan and prove that the functor from earlier descends to a functor from the stable category across the homotopic category into the homotopic category. And so now that endows the growth in the group of the homotopic category with the structure of an OP module. So this gives us a recipe for categorifying modules over the cyclotomic ring. In practice, we have to do, in the examples, most examples that we have to do one further categorical construction. So let's let F be a morphism in the homotopic category between PDG modules. So the fact that F is a morphism between PDG modules, it means several things. It's an A module morphism and also respects the PDG structure. So F is said to be a quasi-isomorphism if it restricts to an isomorphism in the stable category. That means forget about the A module structure, just really think about the PDG structure in the stable category and see if it's an isomorphism there. So one could show that the set of quasi-isomorphisms is a localizing class. And so if we invert all these, if we invert quasi-isomorphisms, we form this derived category. And the functors from earlier descend to a functor from the stable category across the derived category to the derived category. And I see there's a question, yeah, H has a homological degree. It's either minus P or something very close to that. Right, so the growth in the group of the derived category is also an OP module. Okay, and in all the naturally occurring examples, we actually have derivations on our algebras of degree 2. So these degree 2 derivations I'll denote by this partial symbol. And so we could kind of repeat this whole process, and instead of getting the growth in the group of a derived category being modules over OP, the cyclotomic ring, we have this very closely related ring, bold OP. Okay. So sorry, I should just say that the bold OP is Z adjoint Q, and now you plug in Q squared into the Pth cyclotomic polynomial. Okay, and so we saw several examples of Pdg algebras in Chiu's talk. In fact, we saw this actual example. So AN Shriek has a PDG structure. And from Chiu's talk, this was a very special case of these Quiver-Schur algebras arising when you try to categorify SL2 at a root of unity. So AN Shriek has a PDG structure defined as follows. So D on an idempotent is equal to 0. D on this path from I plus 1 to I 0. But D on this other path, length 1 path, from I to I plus 1 could be realized in a couple of equivalent ways. Basically, you append a loop either at the beginning or the end of the path. Using relations in the algebra, it doesn't matter if you append a loop in the beginning or the end. And remember, a loop just has degree 2. So this is a naturally occurring example where we have a derivation of degree 2. And then the small lemma is that the growth in the group of the derived category of PDG modules over A and Shriek has rank n. So each of the n vertices gives rise to a basis element in the growth in the group. Okay. So before I continue, I should just mention that why didn't I start with the algebra AN? And the answer is that AN is a much smaller algebra than AN Shriek. And the degrees of AN are concentrated between 0 and 2. So you don't really have there's no real chance of putting a non-trivial PDG structure on AN. AN Shriek is a bigger algebra, and see here we have a non-trivial PDG structure. Okay, so now I'm just going to kind of repeat some of the arguments that I made in the beginning of the talk about AN Shriek. So again, we let Li be a one-dimensional left simple module. Again, same thing from before. or all elements except for I act trivially, and IL be the corresponding right module. This has a trivial PDG structure. Okay, and when we wanted to construct a categorical braid group action on the AN shriek side, we need to take projective resolutions. And just to remind you, the projective resolution Li had this form. So ignoring the PDG structure, this is what we had from the beginning part of the talk. But now, when we consider the PDG structure, we see that this complex has a bit of a problem. For P is equal to 2, this is actually not even a DG module. One could check that D squared is not equal to 0. And so we have the following key proposition. So Li has a cofibrant replacement. That's just in the DG world or PDG world, it's the analog of projective modules. So Li has a cofibrant replacement, and I'm showing you for P is equal to 2, given by this. So the same objects that we had when ignoring the differential, but we actually have to add this twist from this module, this projective module AM minus 1 to AI plus 1. So we have this extra map there, and you could check that now D squared on this whole thing is equal to 0. And this is the case for P is equal to 2. For general P, one gets a cofibrant replacement by just repeating this middle column P minus 1 times. Okay, and you could check that Li is isomorphic in the derived category to that PDG module. Okay, and so now we let UI be Li tensor IL, and all these tensor products should really be derived tensor product. So these bimodules Li satisfy temporally Lieb relations. So if I and j are far apart, UI tensor Uj is the same thing as Uj tensor Ui. UI tensor itself produces 2 copies of Ui. And again, I'm ignoring some grading shifts. So there's internal grading shifts and homological grading shifts coming in the story. And if I and j are adjacent, you have this temporally Lieb relation Ui, Uj, Ui is isomorphic to Ui. And so using these resolutions or these cofibrant replacements, this is how you prove these temporally Lieb relations. Okay, and then similarly we have a braid group action. So like we did in the beginning part of the talk, we form this complex Ti, which goes from AN shriek to Ui, and then we extend Ui P minus 1 times to make this a P complex. And Ti prime, which goes from the other way, Ui extended P minus 1 times to AN shriek. So these are 2 P complexes. And with Chiyu, we proved the following theorem a few years ago. Well, again, this is just restating what I said before. The growth in the group of the derived category of AN shriek is, I'm just stating this in more representation theoretic language. It's the second lowest weight space of V1 tensor n, where V1 is the standard SL2 representation at root of unity. And these functors Ti and Ti prime, they satisfy braid group relations. So we finally have a PDG braid group action. Okay. So I don't know if I missed any questions in the chat, but that looks to be taken care of. Okay, so this is kind of a signal that hopefully some topological applications could come from this Pdg theory as was envisioned by Hamanov to realize Crane and Frankel's categorification program. All right, so for the next section, I want to talk about a Pdg structure on the deformed Webster algebra. So we could view this, what I just talked about, as Pdg and shriek or Pdg Webster algebra. And what about in the deformation? So maybe a year ago or a few months ago, Yonezawa equipped Webster algebra with the deformed Webster algebra with a Pdg structure. So D of this red-black crossing produces a black dot, and D of this black-red crossing produces this red dot. D of one red dot is 2 red dots, and D of one black dot is 2 black dots, and then you extend by linearity and the Leibniz rule. I should have said that before when defining the Pdg structure on A and shriek. Okay. And so it's easy to see that this map epsilon I from Wi to W from earlier in the non-Pdg section is a Pdg map. this was the unzipping map. You take the thick red strand and you could unzip it into two thin red strands. However, there's a problem map in the direction when you go from the bimodule over itself to this kind of sorgal type bimodule. This is no longer a PDG map. And using an idea of Hovanov and Rosansky from their paper of constructing a Vid algebra action on triply graded homology, one has to kind of expand our idea of what bimodules we should take. So we construct a new PDG module, Wi to the minus E1. So that E1 we should think about as symmetric, the first elementary symmetric function in the red dots, on the I and I plus first strands. Okay, so what is Wi to the minus E1? So as a bimodule, it's the same as Wi from before, but now the PDG structure is twisted a bit. So D on this bimodule generator produces the first element dots and dots corresponding to the first elementary symmetric function on the I and I plus first strand, also with a negative sign. Okay, and one could then check that the map, sorry, let me go back, that this map I to I, which was a problem without the twist, now becomes a PDG map with the twist. And so now we could construct complexes again, P complexes, Ti and Ti prime, and work in progress with Chiyu and Yonezawa and I don't want to get too into this, on the relative homotopy category of W modules, PDG modules, Ti and Ti prime satisfy these braid group relations. So I'm just trying to see how I'm doing for time. Sorry, yes, I have some time. So just want to talk a little bit about the proof of this theorem. So in order to prove this theorem, we need another type of bimodule, Wi plus 1. So this is like a sorgal bimodule for 3 red strands. Okay, so this corresponds to a certain indecomposable sorgal bimodule. So in this picture, 3 red strands merge into 1 thick red strand. And you have similar relations with the black strand. If the black strand slides through the thin red strands, you could slide it all the way up to the top. Similarly for the reflections. And also you have symmetric functions in the red dots slide through the whole picture. Okay, and then one needs to prove the following proposition. There's a short exact sequence of PDG bimodules which splits when you ignore the PDG structure. So in the middle part of this short exact sequence is Wi tensor Wi plus 1 tensor Wi. The left-hand part is this very thick bimodule, and on the right is this twisted bimodule Wi. Okay. And so this is the key proposition to prove. And in order to prove this proposition, so there are kind of obvious maps, but in order to prove that this is an exact sequence, you actually need to find bases for these bimodules, which is a little challenging. And I'll just kind of show you what happens for the simplest of these bimodules. So for, and I'm just going to kind of focus in on the interesting part of the bimodule, where 2 red strands merge into a thick red strand. So what does a basis look like? Well, top, you're free to put anything you want. If the black strand swings to the left, you could put either 0 or 1 dot on the bottom left, and you could put any number of dots on the black strand. On the other hand, if the black strand swings to the right, you're kind of limited. You can only put red dots arbitrarily up top, and anything else will give you a linear combination of other elements. Okay. And so this is, so one proceeds in a way like this to find bases for the other bimodules in this short exact sequence, and one does a dimension count to prove this is exact. And so then, if you wanted to prove the braid group relations, one tensors out the Ti plus 1 Ti, you get this this kind of cube, and using that exact sequence, you reduce that cube kind of slowly to a cube which looks like this, and one notices that this this complex is now symmetric in I and I plus 1. And so then that proves that ti plus 1, ti plus 1 ti is isomorphic to ti plus 1 ti plus 1. Okay.
Well, actually, just a quick question, because it doesn't, because when you swatch I and I plus 1, can I just go back? I'm just curious about something.
This slide?
The short exact sequence.
Yeah.
If you swap I and I plus 1, does the short exact sequence swap?
I believe so.
So it's like,
oh, no. Wait, sorry. Let me,
I suppose
I
you
have
still
to
get
think
the
of-
same minimal complex.
yeah.
I'm just curious. So if you do swap the order I and I plus 1, does the order of the short exact sequence reverse?
You're asking if it goes the other way around?
Mm-hmm.
I don't remember.
Okay, that's fine.
Okay, I could talk.
Sorry.
Yeah. So, and I don't know how much more time I have, because I have another section, but I could also omit it if there.
You've still got 4 minutes.
Okay, so I'll quickly kind of wrap this up with this last section. This is joint work in progress with Ben Cooper and Gio. So, so as I said before, looking for a PDG structure on the algebra AN that we started with, or essentially the zigzag algebra, is problematic because it's kind of too small to have non-trivial P differentials. Okay. Well, what one could do instead is try to take some sort of version of Pdg Koszul duality of Pdg AN streak. Okay. And so we need cofibrillant replacements of all the simple AN streak modules. And we actually saw that earlier. We saw cofibrillant replacements for L1 through Ln minus 1. I didn't talk about the cofibrillant replacement for Ln because it's not necessary for the braid group action. It's a little more complicated, and we actually at the moment only know it for P is equal to 2 in N general, or general P, but we need to restrict to N is equal to 3. So it's a little interesting. So what does it look like? So without the PDG, without the P differential, the projective resolution of Ln just has this circled part here. To get actually a Pdg resolution, you have to throw in all of these other modules. They cancel out in the Grothendieck group, but they're necessary to actually construct a cofibrillant replacement. Okay, so using this in the early relations, one could compute an endomorphism algebra of L1 plus all the way up to Ln. So this is a Pdg algebra, and in some sense one could think of this as a Pdg Koszul dual of Pdg AN streak. And if we throw away this kind of complicated note just for simplicity, let me call Zn tilde the endomorphism algebra of these of L1 plus Ln minus 1, and one could compute that this algebra, and let me also restrict the P is equal to 2 for a moment. This algebra Zn tilde, it's a quotient of this path algebra. So it looks a lot like the zigzag algebra, except that we have an extra generator of degree 0, hi at each of the nodes. And we have the following relation that these extra degree 0 generators are idempotents. We have this old relation that taking 2 steps to the left is taking 2 steps to the right, which is equal to 0. And now you have these interaction terms between these extra these degree 0 idempotents and these paths of degree 1. Notice I didn't say anything about a loop to the left equaling a loop to the right, but one could check that d of this idempotent of degree 0 is equal to ii minus 1i, which is a loop to the left, plus ii plus 1i, a loop to the right. So you're kind of killing it with this homotopy. So that's how you kill this this relation. And so the homology of this kind of Pdg enhancement, or this dg enhancement of Zn tilde, is the actual zigzag algebra. And one last thing to note is that this dg algebra Zn tilde is not formal. There's actually infinitely many higher relations, and for example, here is an M3. Okay, so I think here's a good place to stop.
Fantastic. Thank you, Josh. Are there questions? That's really cool.
I want to ask Josh about the question I asked in the chat, even though other people asked about it. Is that okay, Josh?
Yeah, sure.
I think it was on like slide 38 or something like that.
Okay.
Where your theorem was with Chio.
Oh, yeah. Yeah.
Yes. Okay. Whoops. 36. Okay. Right. So this right-hand side, this V1 tensor n, etc. So there's no dependence on P.
Correct.
There, but in the left-hand side, there's definitely P underlying, and so, like, what's my takeaway from that, or like, what should I? Is that surprising? Like, should that be expected?
I know. I mean, it's basically just tensoring two Weil modules for the small quantum group together, yeah. No, no.
I'll say. I mean, in all descriptions, this is just how you describe a cone, right? So in all cases, for any P, this is the cone of a map between two things. So that description is also independent of P.
Yeah. Sorry, Monica, are you asking about the Grothendieck group question or about the braid group action?
The Grothendieck group question.
Yeah. So I mean, I think it's just like it's just if you just tensor the two-dimensional representation for small quantum vessel 2, you could just you look at the second lowest weight space and it just has the same dimension independent of P.
Okay. Yeah. Okay.
And it's just, I mean, this is,
yes,
I mean,
because it's a Weil module. Okay. Yes. So you don't see. Okay. Right. Now I get it. Now I see why you shouldn't expect P to enter. Okay.
And I didn't construct the categorical actions of E's and F's, where you would get E to the P is equal to 0, F to the P is equal. This is just a weight space. There you would start seeing root of unity phenomena.
Mm-hmm. Okay, and that's, I guess, Ben Webster was saying that since there's no statement about action, in it, you don't see the P. Okay.
Yeah. No. Yeah.
Mm-hmm.
Right. Thanks. In work with Chiyu and also with Michael, we construct the categorical SL2 action. But here, this is just here the focus is just on the braid group action.
Mm-hmm. Thanks.
So this derivation, D, is there any way to think about it in terms of, I don't know, category or geometrically or?
Yeah, that's a good question. I don't know an answer to that. Yeah, one could ask like where these, do these P differentials come, from geometric representation theory or even symplectic geometry, where a lot of these braid group actions for AN come from. What's the analog on the AN side?
I feel the P derivation here. What we're looking at is the first Frobenius kernel of the additive group. That the HP is exactly the algebra of distributions, the group algebra. That's the dual to the coordinate algebra, and okay. which has a half algebra structure. So that's what you are doing the tensor products using that's where the derivation is coming from.
Yeah, that's right. In all these cases, it does lift over Z to an action of this half algebra.
Mm-hmm. Yeah. But I have two questions.
Where does that action come from?
Mm-hmm. Well, the one part is this P, and of course that I would be interested in not just the P derivations, but the P to the Rth power. P is still prime, but could have higher powers. So in this case, whether I should be taking the higher order of Frobenius kernels.
Sorry, go ahead.
Sorry, I'll be quiet.
Yeah. So what will that give?
I think that might just also depend upon the grading convention on the degree of the derivation. If you want a higher P to the, if you want P to the R. I don't know.
No, all these derivations are defined in the integral forms of the algebras, and they're all have divided powers defined on the integral form of the algebras.
That's exactly where the distribution algebra is defined.
Exactly, that's what I'm saying. All these things are equivariant over this big infinite dimensional Hopf algebra. The only reason that they specialize to finite characteristic P is because they don't. There's currently no homological algebra that works for this for GA, for this distribution algebra on GA. I'll mention that all these things actually have an action of SL2 actually. This entire giant Hopf algebra, where this is the raising operator. But again, you asked the question, where does this come from geometrically? And I don't think there's any explanation geometrically for this action yet.
And my second question is about here you can see it started from the A type A quiver. So giving this braid relations or typically algebra relations, these are corresponding to the type A braid group. And you could have other type of Koszul systems, and you also have the circle bimodules corresponding to those. So whether you can also produce the similar type of algebra A, similar to AN for other types.
Yeah. So I mean, without the Pdg structure for like ADE type, you should be able to have braid group action. I think that, well, again, you have to then go to the Koszul dual to have non-trivial Pdg structures. So I think things will carry over for ADE. And as for Sorgel bimodules, so this paper of Pavanov and Rosansky, where they construct a Witt algebra action, essentially kind of, well, one of their Witt algebra generators is their P differential. They work in characteristic 0. And so there is a story where you could kind of start importing Pdg theory into the braid group action from Sorgel theory. But yeah, I don't know about other types. So.
Any other questions? If not, let's thank Josh again.
Thank you.